I will not talk about anything that stands in relation to VR or augmented reality. In addition, I will not use deprecated nodes, like for example the animation tree player, and of course I will only use nodes that can be instanced in the editor, which means I will not talk about the cull instance node, for example, since these only serve to be inherited from other things, like for example in the case of CSG primitive, you have these nodes which inherit from them. I will also not talk about a tilemap2D node, since to me it seems like almost every second 2D tutorial you will find on YouTube is about the tilemap2D, and I have never used it. I am definitely not in the position where I'm going to be the one who tells you something about tilemap2Ds, but the rest of the nodes counts. That the detail in which I'm going to discuss them is dependent from, first of all, how interesting I find them myself, how interesting I think you are going to find them, and how well I actually understand the technical side behind them. Every node you will find will inherit from the default node. It has a lot of functions, properties, and methods, some of which include the find node. This will basically, in my case, look for a child node with this name, regardless of if it is a first level child or a grandchild. Also, it might be interesting to know that if you execute a get parent function on your root node, or basically the first node you add, you will always get a root new viewport. If you want to get the parent from the root viewport, you will get null. Also, if you want to check whether a node inherits another node, like in this case, for example, AnimatedSprite, which inherits from node 2D, it will recognize this as true. The default node also has the property editor description, which basically is a text that will be shown whenever you hover the node itself, even though you might have to reload your scene. The animated sprite and the normal sprite are two very similar nodes. There is one main difference in how you set them up. The animated sprite requires you to create a sprite frames texture in which you can add in images as your frames, align them in whatever order you like them, and even create multiple animations in the same sprite frame. Properties like frame, speed scale, playing, centered, offset, flip age, and flip V should be pretty self-explanatory, and you can also find them on the normal sprite. Sprite is supposed to display one texture in the 2D space, but it is also able to animate not in the form of sprite frames like with the animated sprite, but rather with a sprite sheet like you can see here. This one is one image that contains multiple frames, and under the animation tab you can set H and V frames so that the sprite knows on how to navigate through the frames and display them one by one. In addition, the sprite also supports normal maps. The region property is used in order to simulate a bigger texture than the image you use, or to only use a small part of the image you use as a texture. For example, if you have an image with repeat enabled, you can select a region under the texture region tab if you have a region enabled, and the texture will repeat itself over and over again in this region. Sprite comes with 4 integrated functions, namely convert to mesh, convert to polygon, create collision polygon sibling, and create LightOccluder. Regardless of which action you choose, you will have this pop-up menu window that will let you choose simplification or shrink or grow parameters, and lets you create a preview of how the result is going to look like. Now let's talk about normal maps for a tiny little bit. In this case, I have a sprite with a texture set to a normal map so that you can see what it looks like. This one is integrated noise texture, so nothing really special. And in this sprite I have selected, you can see I set this texture as a normal map. And if I now was to move my light node, you will see that whenever it illuminates the texture, it will come with this depth effect. It actually shows better if I turn down the energy on the light node. The area 2D has rather self-explanatory signals. The monitoring property and monitorable property are nothing else than basically enabling the area to detect or be detected by other areas. The priority property is in which order areas are going to be processed, which is important if for some reason you need one area to be processed before others get processed. There is a physics overrides tab in which you can configure the area to act as some sort of space overrider or gravity overrider, which means that it will change the way physics bodies react to gravity inside this area. I have one area 2D with space override set to combine and a gravity of 2000. Another one in the shape of a rectangle, which replaces the space and has a gravity of 98, so the default gravity. Another area set on combine with gravity of 2500 and mark the gravity vector. And one very similar with also a gravity vector, also on combine with gravity set to 6000. I'm really quick going to explain what's going to happen. Namely, the areas with space override set to combine will combine the gravity I set with the default gravity of 98 and push everybody inside into the direction of the gravity vector. The rectangle with replace will completely prevent any gravity from affecting the rigid bodies except for its own 98, and the two round areas on the right side will push rigid bodies into one direction because I have set a very high gravity and a gravity vector that is pretty far away, so they will shoot any rigid body that enters them into one direction. Now I'd like to talk about the area's capabilities of overriding audio buses. In this example, you see I already have added an audio bus called effect, and you might have already noticed the default bus layout.res, but don't worry, this automatically comes the moment you change your audio bus layout. So I will really quick add in a new audio bus for this example, and you will already see each of them has a name and an output. In this case, the master goes to the speakers, effect and custom both go into the master. You can add effects for each audio bus, which I'm going to do real quick for my custom audio bus here. And to quickly explain the scene, I have an audio stream player which is not playing, which does nothing, it is just here for different purposes. The listener 2D is disabled, so don't worry about this one. The audio stream player 2D follows a sprite and is on autoplay, and the sprite follows the mouse so that you can see where the audio is coming from. As you can see, it has the option to override an audio bus and to which audio bus it should be overridden. In the next scene, I would like to talk about the KinematicBody2D, the StaticBody2D, and a little bit about collision shapes. First of all, the KinematicBody2D's main role is to provide us with two main movement functions, move and collide and move and slide. I have created this player script which lets me change between move and slide and move and collide. And you see I will now be using move and slide, and whenever I collide with a body, the KinematicBody2D will just slide along the edges smoothly. When using move and collide, there is almost no such thing as sliding, since your character will almost immediately come to a stop. The kinematic body comes with two properties: distance, that is being calculated on top of the collision shapes, A static body can use a physics material override, which is basically a physics material that will change the way it interacts with other bodies. As you can see, there are red arrows in my collision shapes. These arrows appear whenever I enable one-way collision, which basically turns them into these things from Super Mario. It basically means the character cannot collide with the body into the same direction the arrow points. There is also a one-way collision margin, which basically snaps the player on top of the collision shape the moment it comes too close to the edge. The collision polygon works exactly the way you would imagine it. It is completely similar to the normal CollisionShape2D, which already comes with inbuilt shapes, while with the collision polygon you are able to draw your own shape. Next node is the rigid body 2D. I have created this scene with a lot of rigid bodies, each of them with two sprites, one of which is used to show you the rotation. The rigid body comes with different modes: rigid, static, character, and kinematic. Rigid is the normal mode, which means it is going to be normally affected by physics. Static basically turns it into a static body. Same with kinematic. And the character mode doesn't allow rotations. Also, the left rigid body you can see is getting an impulse into the direction of my mouse whenever I left click. You can see the character body will not move regardless of how much I ram into it. I apply a lot of angular velocity to the left rigid body from the very beginning. This also works with character rigid body nodes. You just don't receive any angular rotations from normal collisions. Mass and weight are directly tied to each other and should be pretty self-explanatory. The rigid body also has a physics material override in which you can place a physics material. This will define new behaviors for the body, like for example bounce. You can also apply a physics material to a static body, even though admittedly I haven't found out what this is supposed to do. Rigid bodies normally are in a sleeping state, which means no calculations are being performed on it. And with the can sleep option enabled, it will automatically go to sleep whenever it is not involved in any sort of movement. You can manually set it to sleep, in which case they will stop any movement. If we inspect the properties of the rigid body in the remote editor, you can see that its applied forces will always update with its movement in the world. Whenever you increase the gravity scale to a high amount, it might happen that the body clips through collision shapes. In this case, you can set a continuous CD, which will be used to not only calculate its new position, but instead also calculate the way from its last position to its new position, so that there is no danger of running through objects. Especially likely to happen when the rigid body moves with high velocity. The Audio Stream Player 2D is similar to the Audio Stream Player, with the only difference that it playbacks audio from a certain position within its 2D space, which means you can hear from which direction the sound is coming. Both audio stream players have self-explanatory properties like playing, autoplay, stream paused, etc. The audio stream player 2D also comes with stuff like max distance and attenuation. Max distance is the maximum distance in which the sound can still be heard. So as you can see, if I go outside 200 unit radius, it will no longer play back its sound. And the attenuation is basically the sound fall off, or the shape in which the sounds fall off whenever you come close to the maximum distance. Under the audio bus property, you can choose in which audio bus you want the audio stream player to put the sound. The audio stream player has no position, which means The audio can't be played from a specific direction, and instead it is just like a music background, for example. The next node is the backbuffer node. The backbuffer node works with every canvas item derived node, so basically node 2D and control nodes. In this scene I have set up a background image and two shader effects, one blur and one mirage, both of which have their own rectangle. And as you see, the one that is the latest will be the more dominant shader. So if you want to render both of them, you will use a BackBufferCopy. Don't be deceived by the rect you can move, because this is only visual. For some reason it does not work. Instead you have to set the rectangle coordinates manually, or you just use the viewport mode over the whole viewport. You can also go with the rect solution, of course. In which case you will see you have to manually set the coordinates, the width and the height in order for it to properly work. Next up I will be talking about the Skleton2D and the Bones2D, both of which are used in combination to achieve 2D deformation effects similar to those of a skeleton. Start by adding a Skleton2D node and by adding polygons. These polygons will carry the texture. Drag the texture into the texture slot, and then you will manually have to UV paint part you want to have displayed. Sadly, from what I know, this process is not very matured and there are not a lot of tools that can help you. This process for all the other shapes you want to have in your skeleton. In my case, I will only draw one arm and the torso, because this is only to show you how it's done. After you are done with painting the points for the texture, you will have to internally connect them to polygons required so that Godot knows which area of the texture should be deformed in case the neighboring vertices are being moved. Again, you have to repeat this for each component. After you're done, you can start by adding bones to your skeleton. A bone is only a two-dimensional point with a length and a rotation. So don't be fooled and don't think that it has 2 points. It is only one. The length is therefore only a visual representation of the bone. Line the bones along your skeleton the way you intended it. Also, don't forget to name your bones correctly. You might notice this configuration warning next to the bone. This is because it has no rest pose. Go to the skeleton and set the current pose to be the rest pose. Whenever you move the bones, you can reset the skeleton to its rest pose in case you mess something up. After you are done adding in the bones, go back to your polygons, go under the Bones tab and press Sync Bones to Polygon. Now the vertex painting phase of the rigging process. You can see on the side which bone affects which vertex. Those affected will be colored white. Paint the vertices accordingly to the way you want to have them affected. Repeat this process for every single bone and for every single polygon. And once you are done, you can see that the bones deform your mesh. Godot offers a Particles2D and a CPU Particles node. The reason for that is because on Mac Calculations for particle transforms are not calculated on the GPU, which makes the process a lot slower. The Particles2D node uses a particles material in order to draw particles in the world, while all the options the particles material brings are already integrated in the CPU particles node. You can actually copy the settings from a particles material into a CPU particle node. The Camera 2D node is used to change the screen's position. With the anchor mode, you can change whether the parent node of the camera should always be in the center or in the top left corner of the camera. Rotating allows its parent node to push its own rotation onto the camera node itself. The zoom is pretty self-explanatory. You can also use negative values to flip the image. If you have vertical or horizontal drag margin enabled, the camera will only move in this direction whenever its parent node is not inside of a specific margin. The limit is a property that disables the camera from moving outside these boundaries. This is especially useful if you don't want the camera to see out of map. If you have smoothing enabled, you can set a speed value with which the camera will follow its parent node. The CanvasModulate is a super simple node. What it does basically, it changes the color of every 2D node that is within its canvas layer. Each canvas layer can have up to one CanvasModulate node. The moment you want to add in a second one to the same layer, it will throw a warning which basically tells you that the first one created will work. Joints are being used to connect two physics bodies and make them behave in specific ways. Like for example with the pin joint, to sort of pin one body to another object from which it cannot distance itself. The damped spring joint 2D is very similar to the normal pin joint 2D. Offers a length property, which is basically how far the second body can move away from the first body. A rest length, in case nobody moves. The damped spring joint 2D will try to make both bodies rest in a certain distance from each other, namely the rest length. And the stiffness is basically how hard the node is trying to move them to the rest length. The groove joint is very simple to understand and comes with two properties. An initial offset, which is basically the position of the object within the groove, and the length, which is the length of the groove itself. The Light2D and the LightOccluder2D are both very neat nodes. In this scene I've set up a sprite as a background so that you can actually see the way the light is illuminating my scene. Light node comes with different modes, one of which is the add node, which is also the default mode. In this one, the color values of the light will just be added to everything that it illuminates. A light occluder is basically a shape you can set or convert from a sprite that serves as an object that collides with light. Shadows are not enabled per default. If you want shadows to be cast, you have to enable it on the light node. As you see, the shadows are very sharp. If you want to have smoother shadows, you can use properties like gradient length or filters. The Light2D node also has a height property, which is used to simulate illumination effects together with the normal map. As you can see in this example, greater the height, the more is being illuminated. You can also change the light's energy and color and even shadow color. Okay, you can use the mask mode, for example, to hide objects in the shadows. Another way to achieve a similar effect is with adding a new canvas item material to a sprite and setting its light mode to light only. In this case, only parts of the sprite will be visible that are currently being lighted. The Line2D node. This node surprisingly draws lines. You can set a width for the whole line or use a width curve to dynamically change it as the line progresses. You can also set in a texture and let it stretch along the whole line or use it as a tile. This of course implies that you have repeat enabled in the textures import settings. In the border section you will find options for anti-aliasing and for creating smoother corners. Whenever you hear sound coming from AudioStream Player 2D, you will notice that if it is on the left side of the screen, the audio will be emitted from your left earphone, while the same applies for the right side, and the music will come from both sides whenever the AudioStream Player node is in the middle of the screen. The listener node is used to override the position from where audio is heard from. For example, if you were to place it on the left side of your screen, you will always hear the audio coming from the right side, because for the listener, the audio stream player is always on its right side. So now I will be talking about the MeshInstance2D and the MultiMeshInstance2D. First of all, you might already know that the Mesh2D is very similar to a sprite, and you can actually convert a sprite to a mesh, but you might be thinking, why would I want to do this? The reason for that is, especially if you are using large sprites with a lot of transparent pixels, these will still be rendered whenever the game runs, which means that especially on mobile, this can cause bad performance. So by converting a sprite into a mesh, you can prevent the rendering of transparent pixels. The MultiMeshInstance2D is used to populate an area with 2D meshes. The reason why you want to do this is because the way Godot renders objects, it gives each object its individual draw core, which takes up a lot of time, but the multi-mesh combines all of these different meshes into one, which means they share the same draw core, which saves a lot of processing power. If you have ever worked with the multi-mesh in 3D, you will know that you have your separate window in which you can choose which surface you want to populate and how you want it to be populated. Sadly, the MultiMeshInstance2D does not offer such luxury, which means you manually have to set this up in code. And this is the way how you do it. First of all, you need a reference to your mesh instance, which you want to use to populate an area, and a reference to the multi-mesh. What this script does is basically whenever I press the left mouse button, it will execute the create function. The way this works is you have to assign your raw mesh from the mesh instance into your multi-mesh instance slot. Then you will have to declare vector2 for a distribution area. This is the area in which the multi-mesh instance will spread the meshes relative to its own position. Then you will have to iterate over your instance count, which is a property set in the editor. And for each instance count, you will create a transform for the new mesh and then apply this transform. Next in the list are the Navigation2D node and the Navigation Polygon instance node. For this scene, I have set up a Navigation2D node and a Navigation Polygon instance node as a child. In addition, I have added in a line which will later draw the paths I will get from the navigation node, an absolutely useless camera which does nothing, and a polygon which for now also does nothing. Usually, every content you find about the Navigation2D node is always in relation with tilemaps. That's because tilemaps make the implementation of a navigation system a lot easier. In my opinion, the Navigation2D node is a not that well working node, because it feels incomplete to at least some extent, and the system in general could have been much better. Thankfully, it is announced that the navigation will get improvements in general once Godot 4 is out. To explain what is happening in this script, This function doesn't matter for now, already function is pretty empty. In my physics process function, I will get a simple path from my Navigation2D node from the position 2020 to my mouse position. And I will also set the line to the path so that you can see what is happening. Once I will launch the scene, you will know that nothing happens. That's because the navigation polygon doesn't know where it is allowed to move. For this reason, you have navigation polygon instances. Nodes can carry a navigation polygon, which you can, like every other polygon instance in Godot, draw in the editor. And once you close it, you will see that the inside is filled with this green area, or if I disable it, orange. Now, if I was to run this, if I run the scene now, you will see Navigation2D node draws the path from its own 2020 to my mouse position, which in this case is a straight line because it is obviously the fastest way. To spice stuff a bit up, you can draw internal polygons which will automatically be removed from the outside. And it is going to happen exactly what you would expect. The Navigation2D node is only allowed to move in the green area. The problem is that this is very static. So if you, let's say, have a lot of different levels and each of them has different setups of obstacles, you would have to manually draw this over and over again, which obviously is not possible. So instead, we will take a look into the code. The create navigation polygon function does exactly what it says. What it does is it creates a new navigation polygon resource, which is the nav poly from our navigation polygon instance. Then we will draw this outline, which is the equivalent of these 4 points we created in the editor. I will add this outline to the navigation polygon, and now comes the magic. For example, I have made a collision polygon and added it into the impacts navigation group. What the script does, it iterates through every node in this group, and I'm reusing my outline variable I declared up here. And sadly, this only works for collision polygons and not for simple collision shapes, since I'm accessing this vector point array which is used to draw the polygon. What we do is we check if it is really a polygon 2D. If it is a polygon 2D, we want to get the polygon, which is this exact vector. Then if it exists, so if it is not empty, then we go through every single point and we append it to our outline, but not before we xform it. What this function does, function to calculate the collision polygon's transform on top of its vertices. The reason we do this is this vertice data will always be the same, regardless of our position, rotation or scale. So we have to manually apply it with this xform function. We will then add in the outline to our navigation polygon, and once we are done with all the different collision polygons, we want to call the make polygons from outlines function, and most importantly, apply the navigation polygon in our navigation polygon instance slot. So if I now was to run the script, and of course call the function, we'll see we draw our rectangle from 0, 0 to 4000 and 0, and it also successfully removed the polygon from the area. One problem we have though, if we move this collision polygon, then our navigation is messed up. So one thing you can do to counter this is by repeatedly calling the create navigation instance. In my case, I call it every frame, but I would suggest to at least use it with signals you fire whenever you, for example, move one of these collision shapes. For this example, I will also move every single node that is in the impacts navigation group to the left side of the screen. And you can see the object moves and the path is being updated. And you might be thinking that this is awesome and this is an awesome solution for everything, but sadly Godot is very picky when it comes to drawing these polygons. If this polygon was too far on the outside and would slowly enter our area, Godot vomits. So this method definitely has its limitations, but overall it is at least semi-viable solution. The next nodes are the parallax background and the parallax layer. Parallax layers are supposed to have a parallax background as a parent. You can then add in sprites, for example, and I have implemented a scrolling camera. The lights in the background are being moved via code. And the strength of the parallax layer is that you can set an individual motion scale for each layer, which can create pseudo 3D effects. Path2D node is a node which holds a curve. You can manually draw the curve by adding in points in the editor and or smoothing out corners. And the path node is also being returned from the Navigation2D node. It gets funny once you combine the Path2D with a PathFollow node. PathFollow node has an offset property which places the node on a specific part of the path node. This is especially useful for tower defense type games. And of course you can attach children to the Pathfollow2D node, which then makes its children follow a path. The Polygon2D node holds a custom drawn shape which is filled with a default color. Also used for two-dimensional bone skeleton animations. You can also apply a texture to the polygon, in which case it will serve as a mask to the applied texture. Of course, this mask can be inverted. A polygon can also carry data which is needed for 2D skeleton animations, but also a vertex color data with which you can achieve funny looking gradients inside the polygon. Position2D node does literally nothing. It is only used to access its transform which it inherits from node 2D. It has a gizmo extend property, which is basically the size of the cross that is being drawn in the editor. Present you the script. Whenever I press the left mouse button, I will print the current data from the raycast. Body movement function is used to control the kinematic body in the scene. I may present to you the Godot tank. As you can see, whenever I place it inside the raycast and left click, it will print the data corresponding to the function calls in the script. From what I know, a lot of people have a problem understanding remote transform nodes, even though it is a very simple node. As you know, a node pushes its own transform to all its children, which means if you scale the parent node, all its children will also scale with it. The way you have to imagine the remote transform is that it gets an input, which is the transform it gets from its parent, and it has an output, which can be position, rotation, and scale, which it pushes onto another node. I tick position, rotation, and scale, then the node from the remote path will behave as if it was a child of the remote transform node. If I was to untick scale, if I was to only choose rotation, then obviously only the rotation from the remote transform would be pushed onto the child and it would remain in its old position. Same with position. Only the position from the remote transform will be pushed onto the sprite. TouchScreenButton is basically a normal button which was especially developed to be used on mobile, and it supports multi-touch per default. In order to test this scene, in my project settings under input devices pointing, I have to enable emulate touch from mouse. The touchscreen button can carry a normal and a press texture, similar to the normal texture button. Hold down left click in a normal button will not remain pressed whenever I leave it with the mouse, which is not the case with the touchscreen button, which is pressed as long as the mouse button is down. And the visibility notifier node has a shape and it will fire signals whenever it leaves or enters the current viewport. The visibility enabler 2D is very similar to the visibility notifier, only that it comes with specific actions that can be executed the moment the body leaves or re-enters the screen. In order to show you these actions, the KinematicBody2D number 2 has a playing animation player which rotates one of its animated sprites. It has two animated sprites which both have a playing animation, and it also has a CPUParticles2D node and a normal Particles2D node. And you will see all of these will continue the moment it re-enters the screen. As you might have noticed, since the particles node restarts, you can obviously see that the particles just very recently started emitting again. The pre-process property of the particles is very useful, because if it re-enters the screen, you will see it now gives the impression as if it would have never been stopped. You'll note that objects that are very low in the scene tree will be rendered on top. Maybe you don't want that. In this case, you would use a YSort 2D node, because what this node does, while it is enabled, it will sort all its children by its y-axis and change the order in which they are rendered. I don't know why I even tried this, but I rotated the camera to see if it would dynamically change the render order, but as you see, it remains static. Every UI element node you will find will inherit from the normal control node. Real quick about the control node, the anchors are used to position the control's edges on certain positions. For example, if I was to want a full rect, you will see that the right anchor property and the bottom anchor property will change to 1. If I want to center it in the screen, I will set every property to 0.5. The margins are basically the distance between the control node and its parent. For example, if we were to increase the left margin, the left edge of the control node will increase its distance to the left side of the screen or its parent node. Grow direction is important if the control node grows in size. For example, if you have a text area and you write in text and the text itself is becoming larger than the control node itself, the control node has to expand. Size property is a vector 2 and the control node cannot be smaller than its min size. So if I was to rescale that, you will see I will not get a smaller size than this. Tip property is a text that will be shown whenever you hover it with your mouse. If I was to press the arrow keys in a menu while the game is running, it would change the focus to the next control element in this direction. In case you want to set up custom neighbors, you can assign other control elements from your node tree. There are 3 different mouse modes: stop, pass, and ignore. The mouse filter set to stop, the control node will receive mouse button inputs but not propagate it further. The mouse filter set to pass, it will receive mouse buttons but will pass it on to its parent if the event is not handled. Mouse filter ignore, the control node will not receive mouse inputs and it will immediately be sent to its parent. Size flags are important if you set your control nodes as childs of containers, because, for example, if you have fill enabled, the container node will expand the node without pushing any other nodes. And with the expand flag enabled, the parent container will make this node take as much space as it possibly can. The pop-up node is nothing special. It offers 2 signals when it's about to show and when it's about to hide. Per default, pop-ups are hidden. and you can make it pop up via code. For example, in this case, if I was to press move down, I will have this pop-up, and you will see I cannot click any other buttons in the scene while this pop-up is open. That's because I have exclusive enabled on the pop-up. The window dialog is exactly the same as the pop-up, with the only difference that it offers a window title to be set, and that you can close it with the X. The accept dialog is very similar to the window dialog, with the only difference that it can carry a text and has two more signals, namely confirmed, which is fired if you press OK, or a custom signal. You also have the property hide on OK, which means if I now was to run it, it will not hide whenever I press OK. What you can do in this case, you can use on all three of these dialogues the add button function, which creates the button with the text custom button 1, if it should be on the right side or not, and then the event, which you can connect from the dialog to your own custom action function. Confirmation dialog is almost exactly the same. File dialog should be pretty self-explanatory. If you know what a panel is, then you will know what a pop-up panel will do. Basically, it is just a background that behaves like a pop-up. The pop-up dialog serves as a base class for other pop-ups and isn't really special either. The pop-up menu on the other side, the way you use this, you are supposed to add in items via code. And in my case, I add in 2 check items and 2 radio check items. And when I run it and show it, you will see that these exact options are in the menu. Communication works via signals. The container node itself is mainly a base class for other containers. You can theoretically use it in combination with a script, but it is not intended to be used in the normal editor like other control nodes. The container has the sort children signal, which is being emitted every time the container has to sort its children. So for example, whenever you resize or for the first time the menu is being loaded. The AspectRatioContainer does exactly what the name suggests. You can also decide between different stretch modes. For example, if you were to choose cover, then the child will always cover the whole background of the AspectRatioContainer. CenterContainer will, as the name suggests, keep its children within its center. For whatever reason, you could pick the use top left property. Everything will be centered in the top left corner. The HBoxContainer to align multiple control nodes in a horizontal manner. If I was to, for example, set the expand size flag on this one in the middle, this one will make itself as huge as possible. The VBoxContainer is the exact same thing, with the only difference that it aligns in a vertical manner. The GridContainer is somewhat a combination of the HBox and VBoxContainer. It has a column property, which unsurprisingly is used to tell the node in how many columns it should align its children. HSplitContainer is a container that splits 2 control nodes on the vertical axis. You have this slider with which you can increase or decrease the size of the control nodes inside. Container is the absolute same thing, only that it is split horizontally. MarginContainer is a node which is being used to apply a margin on its children. The PanelContainer is basically a panel, but it functions as a container. So it serves as a background, but has the properties of a container and the behaviors of a container. So it is visually a panel. This would be a normal panel. ScrollContainer is intended to work with a single child control, in this case a VBoxContainer, which as you see would theoretically be already outside of its parent container. So in this case you can find the slider on the right side in order to scroll down. Also works horizontally. TabContainer is a very useful container. Basically what it does, it creates a single tab for each of its children, which allows you to switch between its controlled children. If you want to have a more customized TabContainer, you can add in this specialized tabs node, with the advantage that you now have multiple control derived nodes in one tab, instead of having one tab for each node. Container is a container that is supposed to have a viewport as a child, like in this case. You can see in our 3D world, we have one mesh instance and we have two different camera angles. Both of these cameras are children of one viewport. This is especially useful if you want to make multiplayer split screen. GODOT offers a huge variety of different buttons, one being the normal button. You can add a text and an icon to the normal button. With the flat property enabled, it will effectively make its background invisible. Of course, you can add in shortcuts for your buttons. In this case, you just have to type the name of the action into the action field, and whenever you press the action, the button will also be pressed. The check button is, as you would imagine, just a tickable box. Check button is similar to the check box, only that you can switch it on and off instead of just ticking it. The color picker button lets you choose a color. You can enable and disable whether you should be allowed to enter in alpha values. The option button opens a drop-down with different options to pick. In order to add options to your button, you have to manually do this in code. Button is the equivalent to the normal button, only that it has the flat property enabled by default. The button is basically a button that is represented as a text. If you really want to open the link though, you would have to manually open it once the button is pressed. The menu button is very similar to the pop-up menu. It basically opens a menu whenever you press it, and you can add options to the menu in code. Texture button is similar to the normal button, with the main difference that it doesn't have any inbuilt textures and that you have to apply your own images to the different slots like normal, pressed, hover, etc. manually. While the texture button does have a slot for a texture that is displayed when the button is focused, I once ran into the problem that I want to remake the textures, so instead I came up with this little piece of code. Basically what it does, it draws an outline to the button when it's focused. The way it works, it loads a material, which is the outline material, and every time you load the scene, you iterate through every button you want to have highlighted when it's being focused, connect the signal from the button, and use the button and whether it is focused or not as an argument, connect it to the button focus changed function. In the button focus changed function, you check whether it is focused or not and either apply or remove the material from the button. And this is how it will look like in the end. We're going to use GraphEdit and GraphNode in order to create systems similar to those found in visual programming languages or in the Blender shader editor. For this, GODOT provides the GraphEdit node, which serves as a background or area on which the Graph node can operate. The Graph node automatically creates a new slot for every single control-derived child node it has. The slot will appear on the right side in the inspector, and you will be able to set a color and a type to prevent certain slots from being plugged into each other. First time you use this, you might notice that you're not even able to connect slots of the same type. The reason for that is that you have to manually connect them with each other. For this, you are going to use the many signals the Graph node and the GraphEdit node provide. The color rect is a control node with a one-colored background. Stage scroll bar is a bar that looks similar to those you use to scroll on websites, which also uses a range resource. The range resource can be used to set stuff like min value, max value, and of course the value itself, whether it should be rounded, whether it should grow exponentially, etc. etc. Stage value will define the size of the slider you move within its groove. The V scroll bar is the exact equivalent to the H scroll bar, only that it is vertical and not horizontal. Slider are very similar to the normal scroll bars. Progress bar is used to display a bar in the game. for example, show you the progress of loading screens. The spin box is basically a number input field in which you can combine the numbers with text. The texture progress is to the progress bar and what the texture button is to the button. It basically allows you to customize the progress bar with your own images. You can add in an under, over, and progress texture. Under will be the background, the over texture will be laid over the progress, and the progress texture is the bar itself. In case the images are of different size, you will have to use the offset function in order to offset the progress texture. You can also combine multiple texture progress in order to create a more stylized user interface. The texture progress also comes with a huge variety of fill modes. Separator are purely visual elements that visualize a border between different categories, for example. The item list comes with its own configuration menu in which you can set up selectable rows, which include icons and text. Label is used to display unformatted text without any background. The line edit node is a node that is supposed to take text input from the user. With the secret property enabled, you can set a secret letter which will replace every letter in the node, similar to a password input field. Line patch rect is an extremely useful node. Imagine the following case. You create a background texture for a menu that has a border and you want to rescale the menu. You will have to realize that you cannot just scale the area in the menu without rescaling the borders. Line patch rect is the exact node you need for this case. You can set it up to scale a certain part of the texture and leave the border as it is. Panel is a very simple node that serves as a colored background, similar to the color rect. The reference rect is a helper node which outlines its own color with a certain width and color. Can also be limited to show in the editor only. The rich text label is similar to the label. It is supposed to carry formatted text, and if you enable BB code, you can add in text effects by writing the name into the brackets which you insert in the text. The text edit is an area which allows the user to write on. One mentionable property about the text edit is that it can have its own syntax highlighting. In order to set up syntax highlighting, you will have to use the function the node provides you with in code. The texture rect node is used so that you can display textures with the properties of control nodes. The tree node will allow you to create structures like the one you can find in Godot's Add Node menu. Setting up a tree might be a bit complicated, but it is required to create a tree-like structure. Video player node will do exactly what you would expect from a video player node. Sadly, it doesn't support MP4, but it supports WebM, and since it's control derived, it behaves like a control node and is generally used for playing videos. There is quite a misconception about the 3D space, especially under newcomers, namely that it functions similar to the 2D space, only with one new axis, which theoretically is not completely wrong, yet there is a lot more to this new axis, since now it's not only in the example of rotation, the rotation values itself that matters, but also the order in which you rotate an object. I have also noticed that a lot of people have their problems differentiating the local space from the global space. In order to make 3D transformations easier, Godot uses the so-called basis, which is the local transform of the object. In this example I created in Blender, the colored areas of the mesh are in order to visualize local basis vectors. Because if you want to rotate an object in Godot, you will see that you can only rotate the object along its three global axes. If you, for example, rotate an object along the z-axis and then want to rotate it along its local y-axis, which is now in a new position, you will have to use the transform.basis vectors. The global rotate function takes a vector 3 as an argument, which is the axis along which you want to rotate your object. This is where our local vector comes in handy, because now I can use the local x vector as an argument and as our desired rotation x. And you will see that we finally get the desired result. The same, of course, also accounts for movement. The move and slide function moves a kinematic body into the direction of the vector 3 you give as an argument. So if I press the move down action, the body will move along its local x-axis. And if I press action move up, the body will rotate along its local y-axis. The camera 3D serves as a sort of eye with which you can see what is going on in the game. One neat feature about the camera is that it can override the world environment you see. So I will just really quick add in my bad trip environment into the environment slot and you will see nothing changes, but the second I switch the camera preview you will start crying. Also, the camera has an H and V offset property, which both move the camera without changing the transform of the node itself. At my best will, I couldn't quite figure out what the Doppler effect tracking property is for, because it seems no matter which value I choose and how I change the audio stream players, the Doppler effect tracking seems to be exclusively controlled by the Audio 3D players themselves. The camera 3D also comes with a projection property, which means the perspective the camera uses can choose between 3 different perspectives. The normal perspective, which means objects which are farther away from the camera will appear smaller. An orthographic perspective, which means objects don't get smaller when they move further away from the camera. In order to change the display size, you will have to alter the size property on the camera that comes the moment you enable orthographic perspective. The frustum perspective is very similar to the normal perspective, with the main difference that with the frustum perspective can create a tilted perspective. The clipped camera is an extension of the normal camera, with the difference that it fires a raycast from the position 0, 0, 0 to the transform of the clipped camera, and whenever the raycast collides with a collision shape, the camera will be placed within a certain distance from the object. The animated sprite and the normal sprite 3D serve one purpose, namely to display 2D textures in 3D space. It comes with a lot of different properties, like for example bidirectional and with a billboard property, which always lets it face the camera. Apart from that, they behave like normal 2D sprites and animated sprites, which mean you can load sprite frames into your animated sprite, and you can also load sprite sheets into your normal sprite. The difference between the two particles 3D nodes are the same like with their 2D counterparts, namely that the normal particles node uses hardware acceleration, which might not run on older devices but is better in performance. Also, the CPU particles node again holds all the particle properties within the node, while for the normal particle material you require a process material again, which then holds all the properties for the particles. In addition, the normal particle node has more properties than the CPU particle nodes. For example, it can have multiple draw passes, which you can use to draw multiple meshes from one emitter, while the normal CPU particle node does not have multiple draw passes. Therefore, if you were to copy the particles material from the normal particle node into a CPU particles node, you will notice that the information is lost. And of course, you can use any mesh of your liking as a particle. So, about the CSG combiner and the CSG meshes. First of all, there's a variety of CSG meshes from inbuilt types like boxes, polygons, spheres, toruses, and cylinders over custom meshes. The way you can imagine a structure with a CSG combiner and CSG meshes is that the CSG meshes make up one long calculation. In my case, every mesh has a union operator, but if I was to change the operation on the sphere, for example, absolutely nothing to the custom mesh. The reason for that is because the mesh is underneath chief sphere. The subtraction will only work for the polygon and the box. So if I was to move the sphere into the polygon, subtracts itself from the polygon. The CSG combiner encapsulates all the meshes and serves as a result for the mesh calculation. There are three different operations: union, which is explanatory, subtraction, which you can see in the example of the sphere and the polygon, and intersection. So if I was to move the sphere out of the polygon again and set this to intersection, you will see the meshes above will disappear, which is logical because there's no intersection at all going on right now between the sphere and the meshes above it. So if I want to see something, I have to move the sphere back into the mesh so that there is an intersection going on. This type of system is used to prototype fast maps and or levels. Can imagine the immediate geometry node it is very similar to a mesh instance, only that you cannot feed it a mesh directly in the editor and instead have to draw one manually in code. This is especially awesome if you want to, for example, quickly visualize lines in 3D, because sadly there is no 3D equivalent to the Line2D, so instead use the immediate geometry. Meshes in Godot serve as a visual representation of geometry. Godot offers a variety of inbuilt meshes, even though I would heavily recommend using Blender, for example, if you want to import meshes which are more complicated than these basic shapes. If you've ever used imported meshes and needed to create a collision shape for your new mesh, Godot provides useful functions to cover this need. A create trimesh static body creates a static body as a child of the mesh, which has a collision shape that is exactly the mesh you imported. The create trimesh collision sibling only creates the collision shape. The simplex convex collision sibling is a single collision shape with a convex hull of the mesh as a collision shape. Convex hull tries to somewhat encapsulate the mesh. This mesh is not a good example since it has these strands going away from the body, therefore the convex hull looks a little bit buff. So to give you another example, I will use another mesh to show you a better convex hull. If we were to create a single convex sibling, see that this is a way better convex hull, and that is because of the more compact shape of the ship. Simplified I don't know what the difference is right there. If you're not happy with only one collision shape, you can create multiple convex collision siblings. You will notice it take a while, but then you will have multiple collision shapes for different parts of your mesh. And as you might have noticed, it is way more accurate even though it is convex collision. That is because it only tries to encapsulate a part of the mesh this time and not the whole thing. You can also create a navigation mesh from a normal mesh instance. You can create an outline mesh of a certain size from a mesh. If you want to view the second UV slot, you will see that it has no UV in layer 2. In this case, you can UV unwrap it into the second slot, which is required if you want to create baked light map. I have already explained it in the context of MultiMesh2D nodes, but the way Godot renders objects, each object gets its own draw call, which takes time. So the multi-mesh instance is used in order to combine multiple meshes into one so that they can share one draw core. Meshes in 3D is way more flexible than the 2D multi-meshes are, because for 3D you can get your own populate multi-mesh menu in which you can choose a target surface, the mesh you want to instantiate, and additional parameters like tilt or rotation, the amount, scale, etc. to populate a surface in the manner you wish. Soft body node is used to precisely simulate me going to bed after another video editing shift. All jokes aside, the soft body is used to simulate cloth physics. For example, if you wanted to create pillows or maybe curtains, or even a code for a character, you are probably going to end up with a soft body. So the next node is the light map. For this case, I have set up a scene in Blender, which is important to note because we need meshes from Blender to make this work. In my Godot scene, you can see I have the room imported from Blender. The light comes from Godot and is not imported. I have a world environment node, which basically darkens my world so that you can better see the effects of the light, and I have a baked light map. What this node does, you have to create this box shape, which will mark an area in which you want to create a light map. In order to be able to create light maps, we need two things. Actually three. You need the area. Within this area, you tick use in baked light maps for every object you want to use in your baked light map. But most importantly, under mesh, you have to unwrap UV2 light map AO. Now you will need to know that if you try this with Godot internal meshes, this will not work, because if you want to unwrap it, you will notice that the contained mesh is not type array mesh. Using meshes from Blender fixes this. So every mesh you want to include in the light map should be UV unwrapped, so that you can view the UV2 layer. So if you have use in baked light ticked on every mesh you want to include and UV unwrapped into the second slot, you can go back to your baked light map and tweak all the many parameters for the lighting as you please. I have just created random numbers because I have no idea what this does. Then you can press bake light maps. You can see this is how the area looks with a light map, and this is how it looked without. In my case, I have apparently made settings which brighten up the area by a lot. You will have to find something that fits your scene better. One important thing by now was to disable the Omni light. You will see, since the light it was baked into the texture, the monkey is brighter when you look at it from the direction where the light was, because if we now go on the other side, you can see that here is a shadow. The directional light functions similar to a sun. All objects within the same scene will simulate being lighted from the same angle in which the directional light shines. The light rays themselves have no real origin and will always come from the direction the directional light points into. The Omni light is basically a light bulb, and it would behave in such a way. You can adjust the range, the attenuation, which is basically the light fall off. Every light node has the light resource, in which you can change color energy, indirect energy, which is not visible in the editor or in the game, but when you create a light map or use a GI probe, this will be taken into account. The spotlight is exactly what the name suggests. It illuminates an area in a cone-shaped form. The GI probe, such as the reflection probe, are both very similar to the baked light map node, with the difference that they are more dynamic, All three of them I use to create more beautiful lighting, while the baked light map does so in a static manner. The GI probe and the reflection probe are more dynamic. In this scene I have set up an OmniLight and the Suzanne mesh with an emission material, and you will see when I enable the GI probe, especially the indirect lighting looks just so much better. Both the GI probe and the reflection map, such as the baked light map, all need their own shapes in which they operate. The reflection probe works very similar to the GI probe. While the GI probe's strength lies in indirect lighting, the reflection probe's strength lies in reflections. You can already see the moment I turn it back on, there is a visible difference to the reflections in the scene. You not only can, but you are also encouraged to use multiple reflection probes within the same scene and or combine them with light maps and GI probes. Get the best out of the lighting in your scene. Root motion is a technique used for animating objects. What it does, basically, if you have an animation and the character moves out of its position, this might be a behavior that you do not want. Because if you have, for example, a walking animation, it might be undesirable that the mesh walks away from its origin, because you do not want the body to be controlled with an animation player, but instead with an kinematic body, for example. So what you have to do is you need to lock the animation in one place. For this I have created this Blender model. This is my current animation. And I have created this control bone. This one bone has no impact at all to the mesh. The only reason why it is here is because it serves as a parent to the skeleton, which means if I move this bone, the whole skeleton and the mesh will move with it. This is my animation. What these two keyframes do, they only move the control bone. The animation for the roll itself is only in the other bones. So if I was to remove every keyframe, see that mesh is locked into one position. The problem with removing the keyframes is that the transformation is lost. So there is no way to find out how fast this animation would have been moving. So if I export this scene with the keyframes into Godot, you will find something that looks like this. The animation is still here and it moves the mesh. In order to use root motion, we have to add in an animation tree, create our animation node blend tree, and add in our animation. I'm quickly reloading the scene so that it finally sees the animations I have. And if I was to enable it now, you can see the same animation is playing. But under root motion, you can assign one bone, in my case the controller bone, which will be locked into space. So if I apply this and keep playing the animation, you will see it is now locked into one position. The root motion view node itself is just a helper node, which can only run in the editor, which is used to visualize a floor to the animation, similar to this. It has absolutely no use for while the game is running, and will even be converted to a normal node if you start the game. So let's in the root motion view node. For the root motion view, you have to assign the location of the animation tree. The reason why you don't see it moving right now is because there is an error with my axis, but I have figured out that apparently my movement on the x-axis is being mistaken for my movement on the y-axis for whatever reason. So per default it is locked on the y-axis. If I was to unlock it, you will see, if I make this bigger, will move together with my animation. Anyways, since the root motion view is only a helper, you might be wondering then what is it good for? For what do you actually need root motion? Well, the real magic starts with the animation tree, because you can access the get root motion transform via code from the animation tree. And if I was to launch the game, then you see from the output that the transform returned from the root motion view changed. You can use this information to move the parent nodes of the mesh. For example, if you have a kinematic body with the mesh and the animations as child nodes, you would want to use the kinematic body for movement and not the mesh itself, like it would be if you weren't using root motion. It's actually a pretty useful feature. Visibility notifier works exactly like its 2D counterpart. Is mainly used for its 4 signals. You can give the visibility notifier a shape, identify whether this shape is on screen or not. I have added simple movement so that I can move it out of the viewport. And you will see whenever it leaves or enters the screen, the corresponding signals are emitted. The visibility enabler is an extension of the normal visibility notifier. It can do everything the normal visibility notifier can do, but in addition it can also freeze physics bodies and pause animations. To demonstrate this example, I have created an animation player which furiously spins the cube, and you will see whenever I move it out of the camera, the animation stops playing. Note that the reason why it stops spinning while it is technically on screen is that the visibility enabler's detection shape is way smaller than its parent mesh. The area 3D is a non-physical object which can detect other bodies and or other areas. Monitoring and monitorable property are again the same as with the area 2D, which basically disables the area's function to be detected or to detect. Of course, the area wouldn't be an area if it wasn't able to override the audio buses. The area 3D also has a reverb bus, which the area 2D doesn't have. Even though admittedly I could not figure out how this is supposed to work. Maybe this is because I just didn't hear it on the one and only audio example I used. And of course you can use areas to override physics, either by using a gravity point or not. If you're using a gravity point, then everything within the area will be pushed into the direction of the gravity vector. If not, then the same gravity applies over the whole area. You can also create a custom gravity fall-off for objects which are farther away and which shouldn't be affected by gravity as strong as objects that are very close to the area's center. Kinematic body is providing functions which are used to move the body while taking physics into account. I have a script in which I move the kinematic body along each axis. And lock a kinematic body on certain axes. In this example, when I lock it on the x-axis, you will see even though I theoretically move and slide into the direction 1, 1, 1, the x value is ignored and the body is locked. If you lock the body on all 3 axes, then it cannot move. This is especially useful if you wanted to make a 2D game but are using the 3D space, because in this case you can just Y-lock all the kinematic bodies. The static body is very similar to the kinematic body, only that it is not intended to be dynamic, so instead you should use static bodies for not moving static objects which require collisions. So you might be wondering, if it is not supposed to move, why is there a constant linear velocity vector as a property? But that is because while the static body still won't move, it will apply forces to every colliding object as if the body was moving. For some reason, this does not work with Bullet and only with Godot physics. So once we change the physics engine to Godot physics, the constant linear velocity launches the object into the direction of the velocity vector. You can also override the static body's physics material to make colliding bodies bounce, for example. The rigid body is similar to the kinematic body, only that is already being moved by gravity and environmental influences by default. You can also override the rigid body's physics material. What is new to the rigid body that the rigid body 2D doesn't have is an axis lock. This works the exact same way like with the kinematic body. You can use it to lock it on one axis. If I was to Y lock it, it will not move up or down. With a linear X-axis lock, it cannot move left or right from the camera's perspective. You could theoretically also lock the angular axis. In order to move a rigid body, you should use the script function it provides. Should not mistake the physical bone with the normal bone. The difference between the physical bone and the normal bone, as far as I understand, is that you can add in the physical bone to your skeleton in the afterwards, and it will be affected by other physical influences like the default gravity and or areas with a gravity override. You can create physical bones directly from your skeleton node, yet you will see that some of them have a very displaced offset. So to fix that, you set for each bone the offset individually. And then you can call the magical line from your skeleton node. And tada, you have something that at least somewhat resembles a ragdoll animation. The vehicle body node is a node which is used to simulate quick and dirty vehicle behaviors for your game. Therefore, it is not really suitable for ultra-realistic vehicle behaviors, since it also has known issues. It is supposed to be used in combination with the vehicle wheel node. The vehicle body node is not very complex on its own, because most of the magic happens on the vehicle wheel, where you can set tasks like use for traction and use for steering, and the vehicle body will detect and control the wheels accordingly whenever you change the steering and engine force properties. The AudioStream Player 3D node is used to emit sounds from a certain position in the 3D space. The attenuation model is again the sound fall off, so basically how much quieter it gets on which distance. The rest is pretty similar to the AudioStream Player 2D, only that this time we also have option to create an emission angle. What in this case will happen, it will serve as a shape in which the audio can be better heard from, and everything that is outside of the angle will hear a more damped audio. The bone attachment is a really cool node, I like it. In order to use it, you have to add it as a child of your skeleton. Then you can choose a certain bone as a property in the bone attachment node, and it will attach itself to the bone. So basically it is as if it would be a child of the bone, and therefore gets all of the bone's transforms pushed onto it. In my case, you can see that I'm using the front fin far left bone. So if I was to open up Blender and open up the same rig, you will see that if I select the same bone, the position is the start of the bone. There is no offset property, so you cannot offset it from the bone directly. So if you want to have an offset, you add in a spatial derived node as a child to the bone attachment and move this one, because this will work as an offset. The collision polygon and the collision shape are both used in order to be set as a child to physics bodies, so that they can collide with other objects. The collision shape comes with inbuilt shapes you can use for your collision, while with the collision polygon you have to draw a shape yourself. If you want more complex shapes, I highly recommend using the inbuilt functions from the mesh. now comes the absolute worst part of the video, the joints, because I don't know shit about joints and I have no idea how they work. Even after a long time playing with them, I still have no idea how exactly they work. Each joint uses two physics bodies in order to connect them with each other. The way the cone twist joint connects these nodes is by keeping both of them in their individual cone's angle. From what I believe, the generic 6 degrees of freedom joint is used to lock two objects onto certain axes relative to the other body. There is a ton of properties and axes. The hinge joint is one of the more understandable joints. The way it works is it tries to prevent both bodies from coming closer or going further away from the joint, or at least something into this direction as far as I understand. The hinge joint also comes with a motor property to apply movement to the connected bodies, like you can aggressively spin it around. The pin joint seems to be similar to the hinge joint, with the difference that at least it lacks a motor property. The slider joint seems to be the 3D equivalent to the groove joint 2D, so it is basically used to lock a body in its own groove. In order to use the grid map, you require a mesh library. If you want to create a mesh library, you will have to go to Scene, Convert to and Mesh Library. This way it will add in the meshes into a library, which can be loaded in the grid map. And now you can use this to draw meshes on tiles. As you might know, the AutoStream Player 3D displays audio from its own position. You can use the Listener 3D node, which, exactly like the 2D listener, overrides the position from where audio is heard. Per default, the position of the camera will be used to calculate from which the direction the sound should come from. If you have a Listener 3D enabled, then instead of the camera, the Listener node will be used. The Navigation node uses navigation mesh instances as children, which are used to create a navigation mesh, and the navigation node will be able to navigate through this mesh. If you create a nav mesh resource on the navigation mesh instance, there are a lot of properties which will be taken into account for the baking of the nav mesh. In my case, I am creating a nav mesh from mesh instances. So if we were to add in a ground and bake the nav mesh, you will see that there is a new layer on top of the mesh, which is now the navigation mesh. If we take a look into the nav mesh demo project, you can imagine the nav mesh as a sort of layer that is put on top of terrain, through which the navigation node can retrieve paths between positions. So if you were to add in an obstacle, you can see that the navigation mesh changes on rebake. If I put this cube low enough, you can see that now the nav mesh is additionally on top of the obstacle. You can bake some really sick navigation meshes, but keep in mind what I'm telling you in this chapter right now is deprecated since the Godot 3.5 version launched, which brought huge new additions to the navigation in general. The occluder node is used to create shapes into your scene, which will be used for occlusion culling, which means you can use this for optimizing the game, because everything that is behind the occluder shapes will not be drawn like you can see in this example, even though it is theoretically on screen. Since occluder are used to optimize the game and make it run faster, what the engine generally tries to do is to find a certain amount of spheres which are very relevant, which means they are probably close to the camera and of course in the viewport. So not every occluder will be taken into account. If you want to change the maximum amount of how many occluders will be taken into account, you can change this in the project settings. The path node and the path follow node are super simple. The path stores a curve which consists of multiple vector 3 which are connected to a path. The path follow node is always used as a child of a path node, and you can change the offset of the path follow node to make it move along the parent path. The next nodes are going to be used to create a portal culling system. A portal culling system is basically a system which uses rooms and portals. Usually, the game detects automatically in which room the player is located and will only render objects that are currently in the same room with the player. Portals are used as a connection between rooms so that you can also see what is happening in other rooms. For this example, I have set up a room mesh in Blender, which has two doors, and if you align them in a square, each rotated by 90 degrees, you can see you can walk in circles inside the rooms. One possible way of setting up a portal system is by having a room manager, which is probably required in all cases, a spatial node which has to be called room list, which takes room groups and rooms as a child. The rooms themselves are not physical rooms or meshes, but rather convex hulls of every mesh that is inside the room. In my example, I have also added a camera, which I will use for debugging, and two portals, which are both child of room 1. I know a lot of people are pretty scared of portal systems, but while they offer sheer endless customization, they are actually pretty easy to understand. The room groups don't really serve any purpose in this example, but the one possible way of using them is by managing multiple rooms. Like for example, if you have multiple rooms that are on the outside while others are indoor, you could use a room group to group the two outside rooms together, and apparently you can apply world environments to whole room groups. If you have a structure like this, you can use the convert rooms action on the room manager. And that's basically all it takes for you to set up your portal system. You use a portal system to optimize the game by not making it render objects which are currently not relevant for the gameplay. That means only objects which are currently in the same room as the player will be rendered, and you can use portals, for example as windows or as doors, to enable the player to look from one room into another. This is, by the way, also where the spatial gameplay entered and gameplay exited signals come in handy, since they are being fired whenever they leave or exit the gameplay area, so basically the room in which the player is currently in, which can help with further optimizations. In my room manager, I have set a preview camera so that I can show you what's going on in the editor. And when I press convert to rooms, you will see a warning pop up, which basically means that I have rooms overlapping each other, which is potentially dangerous because at some spots in the game, the engine might not be able to figure out in which room you currently are, since some positions in the world are in two rooms or more at the same time. In my case, this doesn't matter really much because this is just to show you how this works. The room the camera currently is in has no portals. This is the reason why we can't see what's going on in other rooms. And you see, only objects within the same room as the camera will be rendered. If the player was to move into another room, then again only this room will be rendered. But in this case you see also the neighboring room has objects being drawn. The reason for that is because, as I've mentioned, I have set a portal in the door, which means the game will know that it can and should render objects that are currently behind the portal. Portals are bidirectional per default, so if I was to move it through the door, you will see that you can also see back into the other room. I have also connected the signals entered gameplay and exited gameplay from room 2, which means whenever the room is potentially visible, it will count as being in the gameplay area. The skeleton node and the bone node are very uninteresting on themselves. Skeleton provides a skeleton updated signal and the possibility to create physical bones, while I'm pretty sure you could set up a skeleton with rig in code. I didn't even bother to confirm, and instead will show you how to set up a fully rigged character in Blender with multiple animations. So I always start out by using a single vertex and applying a skin modifier. I also use the mirror modifier and sometimes the subdivision modifier. Then I can start creating a shape that looks somewhat organic or usable. I have enabled clipping on my mirror modifier because most of the time this makes the skin modifier behave in a good way. Clipping will cause issues if you want to extrude a vertex on the middle axis to the sides. In these cases, I temporarily disable clipping, extrude, and then re-enable clipping. After you are done with your model, you apply all the modifiers from top to down and start in adding bones and creating the rig. Now, some tricks I have learned when rigging characters. You should always name your bones, only rig one side of the skeleton. And if you have your names correctly, like for example everything that is on the right side ends with an _R, you can just symmetrize the skeleton and it will mirror itself correctly and with the correct bone names. Then parent with automatic weights. In this example I will not manually vertex paint and I will take it just as it is. Then we are going to open up the NLA editor, which means non-linear animation editor, and we can start creating our first animation by just normally adding in the keyframes with I. Once we are done with our animation, we go back to the NLA editor, rename the animation the way you want to have it appear in Godot's animation player, and press the button on the right side of the name, which will remove all the keyframes from your timeline and save the animation. You can now start with another animation and repeat the same process. After you are done, give your animation a proper name and add it to the other animation, and press the button on the right side of the name. Save your blend file and give it an appropriate name. Then select your armature with the mesh and export it as GLTF2. And if you now open it in Godot, you will see the animation player has all the animations you made saved with the correct names. The position 3D node does literally nothing. Actually it does less than nothing because the position 2D at least has a Gizmo extends property. The ray cast is a ray which is being cast into a certain direction. You can use it to detect other physics bodies and additional stuff, like for example the angle on which it hit a surface, the point where it collided, etc. etc. The remote transform node works exactly like its 2D counterpart. You can imagine remote transform as if they have an input and an output. The input to the remote transform is the scale, position, and rotation that is pushed from its parent node onto the remote transform itself. And you can choose a node in the remote path, and every property that is ticked under the update section will be pushed onto the node in the remote path. That means in my case, I input the transform from my camera into my remote transform, and the remote transform pushes it onto the static body. For now, I'm only enabling the rotation and the scale, which means if I rotate the camera, the static body will have the same rotation. If I only wanted to update the position, exactly what you expected is going to happen. It will not rotate or if I was to scale it, it would not scale with the camera, but only take its position. I want to present to you the worst node in all of Godot. It is so terribly bad, it does not work properly, it is fully redundant and can be easily replaced with other nodes, and is going to be removed in Godot 4. The proximity group has a group name and a radius. It provides a broadcast function which, if called, searches for other proximity group areas within the grid radius and within the same group, and will call the function which name is used as a parameter in the broadcast. I have a lot of meshes. Each of them has a proximity group as a child. When I press the left mouse button, one of the meshes will remove itself from the scene tree. The spring arm is a really cool node. You might have already heard of the clipped camera, which is basically a raycast that if it intersects with an object, it will place the camera on the place where the object collides with the raycast. This is used so that the camera doesn't look through objects which might stand between the parent of the camera and the camera itself. The spring arm is also a raycast, but it positions any of its children at the end of the raycast. So if I was to place a camera on the spring arm, you will see whenever the raycast intersects an object, the camera will be placed on the end of the raycast. The animation player node is used to effectively animate any sorts of properties on different nodes. You can use it to change any sorts of variables that are bound to a node. For example, you can change scales, position, or transforms in general, but the list goes on and on. You can even animate an animation player with another animation player. You can call functions from your animation tracks, and you can also change variables inside your own scripts. For that, the variable requires a custom setter to be set or something like that. I didn't read into it. I would always go with typing export in front of a variable, because that way you can find it whenever you try to reference it from the animation track. The animation tree node is used to control animation players, or to be more precise, the animations within an animation player. You can use the animation tree to create transitions and or blend animations together, etc. If you are in 3D space, you would usually go with the animation node blend tree, and in 2D you would go with the animation node state machine. Regardless of what you choose, you will find yourself in this animation graph. In the example of an animation blend tree, your own nodes to, for example, add or blend nodes together, while the animation node state machine is used to control transitions between nodes in 2D space. The audio stream player is used to play back audio. It has no position, so it cannot display audio from a certain position. To show you the canvas layer, I have set up this test scene. I have 4 sprites, one in each corner of the screen, and one camera that I can move with my keyboard. I have 4 different canvas layers, one which only has a color rect that has a mirrored shader, and 3 which all have one background, and 2 labels which are anchored on the left bottom and the right bottom corner each. The canvas layer has an index, so it is used to draw different layers in, for example, back and foreground. Foreground is especially useful for user interfaces for while the game is running, like HUD, but you can also add a pseudo 3D effect by enabling follow viewport on a canvas layer and changing its scale to either bigger or smaller than 1. The HTTP request node is used to unsurprisingly send HTTP requests. This is probably especially useful if you are making a non-type game app with Godot, because you can use this to, for example, control database APIs, which will enable you to insert, update, or remove rows from databases if you have a API set up which is reachable over HTTP. The resource preloader is a node which functions as a dictionary for resources. In this dictionary, the name you give the resource serves as a unique key, while the resource itself serves as the value. Apparently, you use the resource preloader as a sort of management node to create a centralized access to resources over the resource preloader node. In this example, I add a material which colors a mesh red to the resource preloader, applied to a mesh which will appear red, but I will then get the resource from the dictionary and change its albedo to green from red. And since the resource is an object, all meshes that use this material will reference to the material which is now green. The skeleton IK node is used to simulate inverse kinematics for 3D skeletons. In order to use it, you add it as a child of your original skeleton node. The root bone and tip bone property are the start and the end of your inverse kinematics chain. The target node can be any spatial derived node, and its transform will serve as a target for the inverse kinematic chain. So I add a position 3D node dedicated to the target node of the skeleton IK, and once you reference it in the target node, you can press play IK on the skeleton IK, and you will see the simulation starts. You usually use a timer node if you want to receive a signal after a certain amount of time. It is not always required to create a timer node, because there is a scene tree timer which can be created in code. You can have multiple scene tree timers at once, and this will save you the node overhead costs the timer would have. A lot of nodes come with the so-called process mode, which usually can be put on idle or on physics. I will show you how this works on the example of a timer. Generally speaking, if the process mode is on idle, it will update after a certain amount of time, and when it's on physics, it will update with your physics frames. For this example, I have two timers, one that updates on physics and one that updates on process. And in each physics process and process function, I print how much time is left on both timers. I have also written a function which simulates lag. You will see when I run this, I get a lot of output overflow errors. So I'm quickly heading to the Godot logs for this specific game in the app data folder, and you will see the first function to be called is the physics process, in which the timer on physics has 29.98 seconds left, while the timer on idle has not yet started counting the time. The second function call is the process function, in which now the timer still has the same time left from the physics frame from before, while the idle timer is now on a time left which is technically lower than the one from the physics frame. I'm now going to do the same thing, but this time I'm going to simulate lag. If I scroll down to the time where the first lag started, you will see that the timers are not real time, and that if your game freezes, the timers will also freeze. Node is used to dynamically interpolate properties of different nodes. In my example, I have added a tween and a sprite node, and in my ready function, I prepare the tween to interpolate the global position of the sprite from its current position plus the position 200, 100 within 4 seconds. If I start the tween with the left mouse button, you will see within 4 seconds it moves 100, 100 from its current position. If we now add in a second line, which moves sprite from its current position to the vector 900, 300 from its current position within 2 seconds. See, after the 2 seconds and the last interpolation ends, it will finish the first one. You can also use tween nodes to interpolate script variables. In my case, I want to interpolate the custom property from the value 1 to 10 within 5 seconds. So if I start this, you will see this is the exact result. You can also use the interpolate callback function, which from what I found out is basically calling a function after a certain amount of time. Viewports serve as windows to your game. In my scene, I have a mesh instance as a child of the root node of the scene, and another mesh instance which is child of a different viewport. The reason why you don't see the second mesh instance in the first world is because the viewport has the own world property enabled, which means even though there are two meshes in the same scene, both of them take place in a whole different world. I personally used the own world property when I created a game where 3D objects were rendered onto 2D sprites, because if I hadn't enabled own world on each viewport, every sprite would have displayed every single object that is anywhere in the game at the same moment. Viewports can also override a world environment. You might be thinking, since you already know that the camera can also override a world environment, which one will take priority? It's the one from the camera. Transparent background will remove everything from the image that is not part of a mesh instance. There is a lot more to say about viewports, but for me this is absolute magic, and I have no idea what half of the properties even mean. But I know that one funny thing about the viewport is that you can get a texture from code and apply it to any other node that has a texture as a property, like for example the sprite or the texture rect in my case here. The environment node is used to store world environments. Only one at a time can be in the scene simultaneously. And this world environment is used to apply post-processing in your scene. It is a very technical node, so I will not be going over the majority of the properties, but I will show you some of the key things I have learned in my experience. First of all, if you want to make 2D sprites glow, you'll have to use a world environment, which mode is set on canvas. Then you have to go to glow and enable the glow, and then under modulate you can change the color picker to raw, and this allows you to enter values that are greater than 1, which basically means everything greater than 1 will be converted to a bloom. So if I now enable glow, you will see it glows. I will speed up the clip in the background so that you can see a little bit more of what you can actually do with, but keep in mind there is huge variety of different environments you can achieve. For 3D environments, you can use sky backgrounds to simulate the sky like with the default environment, or you could go with a clear color background. The fog property is basically a color that is applied on objects which are a certain distance away from the camera. And again, since this is not a world environment tutorial, I will just speed up the background, show you some of the eye-destroying animations I created. But not before I show you the keep background mode, because look at this.
It's happening! Everybody stay calm!
What's the procedure, everyone? What's the procedure?
Stay calm!
Wait.
Everybody
Flow containers are used to hold child nodes and arrange them in a so-called flow, which means it tries to keep all of its children in a line, but in case there's not enough space left, it will break into a new line. This is especially useful if you want to clump a lot of control-derived nodes into an area, which is supposed to work on many different screen sizes. It exists as an H-flow container and a V-flow container. There is also a new label 3D node, which is used to display text in 3D space. Per default, it is similar to an image, but you can also enable billboard, which will make the text always look at you. And there is also a Y billboard mode, which will only rotate the billboard along its Y-axis. The occluder node got new occluder shapes. You now not only have to use a occluder sphere shape array, you can now also use an occluder shape polygon, which is an array of points used to draw the polygon. Now about a new navigation system, and we have huge additions. For 2D and 3D, we both have a new navigation obstacle 2D node and a new navigation agent 2D node. The way it was in previous versions, you would use the getSimplePath method from the navigation node, which is then used to get a path, and with this path you have to manually navigate your object to the target. Now with the new navigation system, the path finding is done by the navigation agent itself. The navigation agent in my case is a child of the kinematic body. A short disclaimer, the way I did it, it works this way. If this is the way it is intended to be used, I don't know. I know there is a lot more to navigation, but it took me close to 3 days to only make simple obstacle avoidance work. And since this is not supposed to be a deep dive anyway, I will just cover the parts I understood myself. To explain the scene, you again manually have to draw the navigation polygon, but this time you can use the obstacle 2D node instead of having to cut out part of the navigation mesh for obstacle avoidance. The way this works, I set the navigation on both my navigation agent and the navigation obstacle to my navigation 2D node. I know I already said it, but the main difference between the old and the new navigation is now that with the new navigation, you have two ways to make your navigation agent work. We use the function setTargetLocation on the navigation agent. That way it will know where it wants to be. Then what you do every physics frame is called a NavigationAgent.getNextLocation function. I will show this, but what this does, you can just trust this function. It will always give you the point on the path it calculates to its target where you want to go next. And so far this has worked very smoothly. What we then do, we calculate a velocity from our body to the target, which will give us a velocity vector. From now on, you have two different ways of working. Now, after you are here, after you have your velocity, the first option you have is to immediately move the kinematic body into the direction of the velocity. So usually, in the case of a kinematic body, you would call move and slide with the velocity vector. This will not give you any sort of obstacle avoidance though. The second option would be to use the setVelocity function on the navigation agent like the way I did it. For this option, it is important that you have avoidance enabled, because if you don't have avoidance enabled, the velocity computed signal will not be emitted. Because what setVelocity does, basically, after you call this function, the next frame it will emit the velocity computed function. And in this velocity computed function, you can then move and slide your body with a safe velocity. The difference between the safe velocity and the velocity we calculated to our next point is that the safe velocity takes obstacles into account. To mark objects as obstacles, you have to create this navigation obstacle on the child of another physics body. What I do in this scene, this is my body, this is an obstacle, and the body moves to the direction of the mouse whenever I left click. So to show you what is going to happen, you will see it goes to the left top corner. That is because now I don't have set a target, and so the default target is 0, 0, 0. So it goes to the part where it is as close as possible to this position. I also have the following information. The target is 0, 0 as I've mentioned, and with the getPath function you see the path that was calculated when you set the target. Target reachable and target reached is pretty self-explanatory. The reason why this is so jittery, and this is also the case in the 3D navigation demo, is because I do always move with the same velocity in the direction of the target, which means if I'm very close to the target and still move with a certain velocity, I might jump over the target, and in the next frame it will do the same. It will jump back and forth, and this is this jitter. The navigation agent has avoidance enabled, and all of the other settings are on default so far, and I'm using the second option from which I told you before, namely the one with obstacle avoidance. On the navigation obstacle I have estimate radius enabled, which means it will automatically estimate the parent's collision shape. If I now want to go on the right bottom corner, you will see whenever the obstacle gets close, it will try to dodge it as good as possible. And this is basically how you set up a very simplistic demonstration of the new 2D obstacle avoidance system. Of course, you can change the way it behaves with obstacles by tweaking all the parameters in the navigation agent. One huge addition to the navigation system is that you now can bake the navigation mesh in code. So if I remove my navigation mesh and go back to my main script, and in my script I'm going to call a bake navigation mesh function. Bake navigation mesh takes a bool as a parameter, which per default is true. If you call it with true, then baking is done on a separate thread, which means it will not block your main thread and can be used in the background. Therefore, it will not lag whenever you create a new navigation mesh, but the downside is that it will take way longer. If, for example, in a loading screen anyways, you would probably want to use the onThread equals false, because that way it will block the main thread, but it will be baked much faster. For my 3D scene, I have set up a navigation mesh instance, which has 3 mesh instances as children. I have a flying camera, which I can control with my mouse and keyboard, and whenever I press the left mouse button, then the global position of the camera will be used as the target for our navigation. The object which should navigate to the camera is this rigid body bar. And I also have added in an obstacle, which is also a rigid body, which should in the best case be avoided. 3D navigation works exactly like the 2D navigation. Again, you use set target location to give a target to your navigation agent. In your physics process, you call navagent.getNextLocation, because that way you can use the position to calculate a desired velocity, and in option 1 immediately move with this velocity into the direction, or if you want obstacle avoidance, make sure that avoidance is enabled on the navigation agent, and then we use the navigation agent.setVelocity, and whenever the signal velocity computed fires, we move with the safe velocity. If you want this to work though, you must set the navigation of the navigation agent to your navigation node, and the navigation of the navigation obstacle also to your navigation node. I also move the obstacle from left to right. You will notice that the sphere will try to move to the position 0, 0, 0. I might also add that in my navigation agent I have set a agent height offset. Because the navigation agent has no position, it might not really know on which height it is standing. So if I was to reset this to 0, you will see the rigid body deep dives into the floor. So if I go back to my navigation agent and give it back the height of -3, you will see it remains on top of the floor as desired. So if I now press left click, you will see the position updates to the position where the camera was when I pressed the left mouse button. Let's try to make it run into an object. You see, it avoided the obstacle that goes left and right. The navigation mesh instance comes with a lot of properties which are used to define how the navigation mesh is built. Like for example the maximum angle which the body can climb. But I would highly recommend playing with the navigation nodes yourself. I have already mentioned it, but it took me close to 3 days, since there is almost no documentation at all to make this work. And in addition, it also seems to be a bit weird, because at some point it either stopped working completely or my signals got disconnected for whatever reason. And since I've only experienced this with the new navigation, I am going to assume, especially since this is a rather new system, that this, for the first time in history, might not be my own fault. So if you want to set up your own navigation scene, create your objects with meshes and collision shapes. And if you want the object to pathfind its way to a target, add in a navigation agent. If you want the object to be an obstacle, add in the navigation obstacle. In your navigation agent, do not forget to enable avoidance if you want to use obstacle avoidance. Connect the velocity computed signal to your script from where you control the body. If you set the target, use set target location. In your physics process, use the get next location. Calculate the direction and the velocity to this location and set the velocity to the navigation agent, and then move in your velocity computed function. I'm also very new to the navigation, so I would just say, now that I have told you how to set up these basic examples, I would highly recommend that you try to play around this with your own, because this is probably the best way to learn. And as I've mentioned, there is a lot more to the new navigation. Like for example, the navigation mesh now also comes with enter and travel cost. For this case, you would have to set up multiple navigation mesh instances and have them as a child of the same navigation node, but I have not found out how you are supposed to make this work, so I sadly couldn't test enter and travel cost, even though I would have loved to. But maybe I will cover this once the documentation actually comes out.